Let's talk about the periodic table. Mendeleev is the father of the periodic table. He was a Russian scientist, but he is not the first one to try to organize things. He's just the one that came up with the process that stuck. And what he did is he took the known elements at the time, wrote their information down on note cards, and then set them out and realized as you went in increasing mass, as you went from one element to the next, they had patterns that repeated. All right? And this is what led to the periodic table. All right? Periodic means repeating pattern. It means a set of repeating patterns or properties. And Mendeleev arranged the elements by increasing mass. Here we see Mendeleev's table, his actual table. All right, because you can see that it's written in Russian at the top. At this point, chemists were using similar notations. All right, if you notice, here we have beryllium, magnesium, zinc, and cadmium. Well, zinc and cadmium aren't in that same family, but we know beryllium and magnesium are in the same family. Here we see fluorine, chlorine, bromine, and iodine. They are all in the same column on the periodic table. Here we see sodium, potassium, rubidium, cesium. They're all in the same column. So these are the ways that he chose. He put the similar properties in rows. We have them in columns today. All right, notice the question marks between zinc and arsenic. These were elements that he knew would have things in common, and he knew that bromine belonged down here with chlorine, and so he left some empty spaces. Now, if you look, it's 68 is between aluminum, or under aluminum and under boron, and it ended up being gallium, and 70 ended up being germanium. So he actually predicted elements. He predicted the elements that fill in these spaces. The elements between zinc and arsenic were gallium and germanium. I just said that. All right, there was a close match between the predicted properties and the actual properties, which helped cement Mendeleev's process. So, how do we organize things today? Well, ironically enough, we do not organize things by mass. Because if you look at mass of a period of, let's see if I got to find a periodic table. If we look at this periodic table, and we look down here, you can see antimony is lighter than tellurium, which is lighter, but tellurium's heavier than iodine. If we had gone by mass, we would have iodine and tellurium switched in different places. But we know iodine belongs with bromine, chlorine, and fluorine because they have similar properties. And Mendeleev knew that too. If we go back, all right. Hang on, I just moved my screen. All right. So, let's look at how the periodic table is organized today. I guess I'll move my picture up here now. It's a roving picture. In the modern periodic table, elements are arranged in order of increasing atomic number. Okay? The elements are arranged in order of atomic number, starting with hydrogen that has an atomic number of 1. We already know that the atomic number is equal to the number of protons in the element. There are 7 rows or periods. We call these periods because they have the repeating pattern. Each period corresponds to a principal energy level, which we've already identified, and we use the letter N to identify it. So this first row is N equals 1, the second row is N equals 2, and so on and so forth. They have more elements the higher we get because we have more orbitals available. All right, the properties of the elements within a period change as you move from left to right. These patterns repeat, and that is where we get the periodic law. The periodic law, when elements are arranged in order of increasing atomic number, there is a periodic repetition of their physical and chemical properties. When elements are arranged in order of increasing atomic number, we just said that. Elements that have a similar chemical and physical properties end up in the same column. So if we go back here, the same column, they have similar properties. All right, we're going to talk about columns later, but next we're going to group things. And we're going to group things by metal, non-metal, and metalloid. Okay? This periodic table uses yellow to represent the metals, the green to represent metalloids, and blue to represent non-metals. You'll see a stair-step line. I will often refer to this as the stair-step line that divides metals and non-metals. All right, metals and non-metals act in certain ways, which is why we classify them this way. Now, you'll also notice that we have some colored numbers. We have red numbers, 1A, 2A, 3A, 4A, 3B, 4B, 5B. These are the numbers that American chemists tend to use. In Britain, they tend to use Roman numerals instead, so they use the blue numbers. The international chemistry people use 1 through 18 for the labeling of the columns. We're going to use the red numbers. 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. Okay? The three classes of elements are metals, nonmetals, and metalloids. As we go across the column, or the period, the properties become less metallic and more non-metallic. The number of yellow squares in the table shows you that most of the elements are metals, about 80%. Metals are generally good conductors of heat and electric current. Copper is second only to silver as an electric current conductor. Copper used in electrical cables must be 99.99% pure. I got the odds. All right. Metals all have a high luster or sheen. This comes from a freshly cleaned or cut surface. The sheen is caused by the metal's ability to reflect light. All metals are solids at room temperature except for mercury. Many metals are ductile, meaning they can be drawn into thin wires. And they're malleable, which is hard to read, M-A-L-L-E-A-B-L-E, because they can be hammered into thin sheets, Q aluminum foil. Nonmetals are the blue compound or elements. We have a greater variation in properties in the nonmetals than we do in the metals. Most nonmetals are gases at room temperature, including the main components of air, oxygen and nitrogen. The variation among nonmetals makes it difficult to describe one set of general properties. In general, well, all right, here's some examples of the variation. Diamonds are very hard. Phosphorus is a brittle solid. That's what's on the end of matches. All right, nonmetals tend to have properties that are opposite to metals. They are poor conductors of heat and electricity. They tend to be brittle, meaning that they will shatter if they are hit with a hammer. Okay? Another thing you might jot down there. Metals tend to lose or gain electrons. in their when they try to react and form compounds. Metals, go back up here to metals, metals tend to lose electrons when they try to form a compound. All right, metalloids have properties that are similar. Under some conditions, they may behave like metals. Under others, they behave like nonmetals. The behavior can be controlled by changing the conditions. Like most nonmetals, pure silicon is a poor conductor of electric current, but under some conditions, like if it's mixed with silicon, the mixture is a good conductor. All right, silicon chips, for example, in a computer. Silicon is also present as the compound silicon dioxide in glass objects, and there's your computer chips. All right, periodic table families. The representative elements. These 7 families right here make up the representative families. They display a wide range of physical and chemical properties. Now, these guys have special names. All right, I need to stop for a moment. Let's name them. Family 1A, right here, has a special name. They're called the alkali metals. These are the most reactive metals, and we'll see some examples in class. 2A are called the alkaline earth metals. 3A, 4A, 5A don't have I have always taught them as the boron family, carbon family, nitrogen family, not names that are hard to remember. 6A are the chalcogens. 7A we call the halogens. And 8A are the noble gas family. All right. This is important. Okay. About done here. Some elements in these groups are metals, some are nonmetals, some are metalloids, most of them are solids, but a few are gases and one is a liquid. All right. Transition metals. The transition metals are the group B elements that are usually displayed in the main body of the periodic table. They go between family 2, the alkaline earth metals, and family 3A, the boron family. They fit in there. Copper, silver, gold, iron are examples of transition metals. Atoms of a transition metal use the D sublevels. We've already talked about electrons. We know that the electrons there are D sublevels. And that's what characterize the transition metals. Now, for whatever reason, I didn't get that picture put in, but I have the picture here. All right. Transition metals are metals in the gap between the representative families. They are all metals, and they tend to make brightly colored compounds. Okay? They all lose electrons. They're variable, whether they conduct heat, electricity, so on and so forth. The bottom 2 rows that appear to just be thrown up there, and I've already shown you a picture of where they really belong, are called the inner transition metals. And those inner transition metals fit right here. Here is where they fit. And guess what orbitals those guys are associated with? Those are our F orbitals. Okay? A couple other things. Everybody above bismuth is unstable. By unstable, that means that the nucleus will change, it will break off part of it, and it will give off radiation. Radiation in the gamma radiation levels in X-rays, very powerful radiation, that's not good. Everybody above 92 are man-made. There's a few others in the periodic table that are man-made, but everybody above 92 are man-made. Okay? A lot of those don't hang around very long. All right. That is what we have for our introduction to the periodic table.